Have you ever looked at a complex polynomial fraction like this and wondered how to simplify it? Many students feel overwhelmed when they see expressions like this, but there's actually a systematic method that makes it manageable. Polynomial long division is a method for dividing one polynomial by another polynomial. Just like the long division you learned with numbers, this process breaks down complex polynomial expressions into simpler parts. The key insight is that polynomial long division follows the exact same pattern as the long division you already know with numbers. On the left, we have regular number division, and on the right, we have polynomial division using the same structure. While the process is similar to number division, there are three key differences when working with polynomials. First, instead of single digits, we work with terms that contain variables and exponents. Second, we always focus on the highest degree terms first. And third, instead of subtracting single numbers, we subtract entire polynomial expressions. Polynomial long division is incredibly useful in mathematics. It helps you simplify complex rational expressions, find factors of polynomials, solve polynomial equations, and it's essential preparation for calculus and advanced algebra courses. Mastering this technique will make many other mathematical concepts much easier to understand. Now that you understand what polynomial long division is and why it's important, we're ready to dive into the step-by-step process. In the following sections, we'll break down each step of the algorithm and work through detailed examples together. The division algorithm is the mathematical foundation that makes polynomial long division possible. Understanding this algorithm is crucial because it tells us exactly what we can expect when we divide any polynomial by another polynomial. The division algorithm states that for any two polynomials, we can always express their division using this fundamental equation. Let me show you what each part means. Let's identify each component. P of x is our dividend, the polynomial we want to divide. Q of x is the quotient, what we get as our answer. G of x is the divisor, the polynomial we're dividing by. And R of x is the remainder, what's left over. Now, there's a crucial constraint in this algorithm. The remainder R of x must either be 0 or it must have a degree that is less than the degree of the divisor g of x. This constraint is what makes the division algorithm work. The remainder must have a lower degree than the divisor or be 0 entirely. This ensures that our division process will always terminate. This might seem abstract, so let's connect it to something familiar. Think about regular number division that you learned in elementary school. When we divide 17 by 5, we get 3 with a remainder of 2. Notice that the remainder, 2, is less than the divisor 5. This is exactly the same principle that applies to polynomial division. The polynomial division algorithm works the same way. We divide our polynomial dividend by the polynomial divisor to get a polynomial quotient plus a polynomial remainder that has a lower degree than the divisor. So remember this fundamental equation. P of x equals Q of x times G of x plus R of x. This division algorithm is what guarantees that polynomial long division will always work, and it tells us exactly what to expect from the process. In the next section, we'll see how to apply this division algorithm step by step when we set up a polynomial long division problem. Before we can perform polynomial long division, we must properly set up our problem. This crucial first step will determine whether our division process goes smoothly or becomes a confusing mess. Think of this like organizing books on a shelf. If you randomly place books without any order, finding what you need becomes nearly impossible. But when books are arranged systematically, everything becomes clear and accessible. The first rule for setting up polynomial long division is to arrange both the dividend and divisor in descending order of their exponents. This means the highest power comes first, followed by the next highest, and so on. The second crucial rule is to include 0 placeholders for any missing terms. If a polynomial is missing an x squared term or an x term, we must write it as plus 0x squared or plus 0x. This ensures proper alignment during the division process. Now let's see how this works with a complete division problem. Suppose we want to divide x cubed plus 5x minus 6 by x squared plus x plus 1. Notice that our dividend is missing the x squared term, and we need to set up both polynomials properly. Step 2. Check if both polynomials are in descending order. The divisor is already correct, x squared, then x, then the constant. But the dividend is missing the x squared term, so we need to add 0x squared. Step 3. Set up the long division format. We write the dividend inside the division symbol and the divisor outside, just like in regular long division. Both polynomials are now properly organized and ready for the division process. Remember, proper setup is the foundation of successful polynomial long division. Always arrange terms in descending order of exponents, and never forget to add 0 placeholders for missing terms. This preparation will make the actual division process much smoother and help you avoid common mistakes. Now we come to the heart of polynomial long division, dividing the leading terms. This step determines the first term of our quotient and sets up the entire division process. First, we need to understand what leading terms are. The leading term of a polynomial is simply the term with the highest degree. That means the term with the largest exponent. Here's our example problem. We're dividing x squared plus 3x plus 2 by x plus 1. Now we need to identify the leading terms in both the dividend and divisor. In our dividend, x squared plus 3x plus 2, the leading term is x squared because it has the highest degree, which is 2. In our divisor x plus 1, the leading term is simply x, which has degree 1. Now we perform the division. We divide x squared by x. When we divide x squared by x, we get x. This x is the first term of our quotient. This is a crucial step because it tells us what to multiply the entire divisor by in the next step. Let me break down this process systematically. First, we identify the leading terms. Second, we divide x squared by x to get x. Third, this x becomes the first term of our quotient. Why does this work? We're essentially asking, what do I need to multiply x by to get x squared? The answer is x, because x times x equals x squared. So our first term of the quotient is x. This step is complete, and we're ready to move on to the next step in the polynomial long division process. Now we reach the critical multiply and subtract step in polynomial long division. This is where many students make mistakes, so we'll go through it very carefully. Here's what we need to do in this step. First, we take the quotient term we found in the previous step. Then we multiply it by the entire divisor, not just the leading term. We align like terms carefully and finally subtract while being very careful with our signs. Let's work with a concrete example. We're dividing 2x squared plus 7x plus 3 by x plus 2. From the previous step, we found that our first quotient term is 2x. Step 1. We multiply our quotient term 2x by the entire divisor, which is x plus 2. Notice that we multiply by the complete divisor, not just the leading term. Now we distribute. First, 2x times x equals 2x squared, then 2x times 2 equals 4x. Combining these terms, we get 2x squared plus 4x. This is the product we need to subtract from our dividend. Step 2. We align like terms. The 2x squared term aligns under the 2x squared in the dividend. The 4x term aligns under the 7x term in the dividend. Step 3. Subtraction. Remember, subtracting is the same as changing signs and adding. This is where many students make sign errors, so let's be extra careful. We start with 2x squared plus 7x plus 3 minus the quantity 2x squared plus 4x. When we distribute the negative sign, we get 2x squared plus 7x plus 3 minus 2x squared minus 4x. Now we group like terms. The x squared terms 2x squared minus 2x squared equals 0. The x terms 7x minus 4x equals 3x. The constant term 3 remains unchanged. Here's what we accomplished in this crucial step. We multiplied our quotient term by the entire divisor, aligned like terms properly, subtracted carefully with correct signs, and reduced the polynomial's complexity. Our new polynomial to work with is 3x plus 3, which has a lower degree than what we started with. Before we finish, here's a critical warning about the most common mistake in this step. Students often forget to distribute the negative sign during subtraction. Remember, when you subtract 2x squared plus 4x, it becomes negative 2x squared minus 4x. Always distribute that negative sign to every single term. Perfect. You now understand the multiply and subtract step. This process of reducing the polynomial's degree is what makes long division work. In the next step, we'll bring down the next term and repeat this process. Now let's work through a complete example step by step. We'll divide x squared plus 3x plus 2 by x plus 1 using polynomial long division. First, let's set up our long division. We're dividing x squared plus 3x plus 2 by x plus 1. I'll arrange this in the traditional long division format. Step 1, we divide the leading term of the dividend, x squared, by the leading term of the divisor, x. X squared divided by x equals x. This x becomes the first term of our quotient, which we write above the division bracket. Step 2. Now we multiply our quotient term x by the entire divisor x plus 1. X times x plus 1 equals x squared plus x. We write this product below the dividend and draw a line to show we're subtracting. Now we subtract. X squared plus 3x plus 2 minus x squared plus x equals 2x plus 2. The result of our subtraction is 2x plus 2, which we write below the line. Step 3. We repeat the process. We divide the leading term of our new remainder, 2x, by the leading term of the divisor, x. 2x divided by x equals 2. We add this 2 to our quotient above the bracket. Step 4. We multiply 2 by x plus 1 to get 2x plus 2. We write this below our remainder and subtract. 2x plus 2 minus 2x plus 2 equals 0. Our final remainder is 0. Therefore, when we divide x squared plus 3x plus 2 by x plus 1, we get a quotient of x plus 2 with a remainder of 0. We can verify this by writing our division as x squared plus 3x plus 2 equals x plus 1 times x plus 2 plus 0. Since our remainder is 0, this means that x plus 1 divides evenly into x squared plus 3x plus 2, and x plus 1 is actually a factor of the original polynomial. Now that we've mastered the mechanics of polynomial long division, you might be wondering, why does this actually matter? Polynomial long division isn't just an abstract mathematical exercise. It's a powerful tool with real applications across mathematics, science, and engineering. The first major application is simplifying complex rational expressions. When you have a fraction with polynomials in both the numerator and denominator, polynomial division helps you break it down into simpler parts. Using polynomial long division, we can rewrite this complex fraction as a simpler polynomial plus a remainder. This makes the expression much easier to work with in calculations and helps us understand its behavior. The second application is factoring polynomials. If we suspect that a polynomial has a particular factor, we can use polynomial division to test this and find the remaining factors. We divide the polynomial by our suspected factor. If the remainder is 0, then we've confirmed it's a factor and found the other factors in the quotient. The third application builds on factoring. We can test whether one polynomial is a factor of another. This is crucial in algebra when we need to determine divisibility relationships between polynomials. We perform the division. If the remainder equals 0, then yes, it's a factor. If the remainder is non-zero, then it's not a factor. This gives us a definitive mathematical test. The fourth application connects to calculus. Polynomial division helps us find tangent lines to polynomial curves and analyze their behavior near specific points. These mathematical applications translate directly into real-world fields. In physics, polynomial division helps solve equations of motion and analyze wave functions. In engineering, it's used in signal processing and control systems design. In computer science, polynomial division is fundamental to algorithms in cryptography and error correction. These applications show that mastering polynomial division opens doors to advanced mathematics and practical problem solving. Perhaps most importantly, polynomial long division serves as a foundation for advanced mathematics. It prepares you for topics in abstract algebra, number theory, and advanced calculus, where similar division concepts appear in more sophisticated forms. Understanding polynomial long division gives you a powerful mathematical tool that extends far beyond basic algebra. Whether you're simplifying expressions, factoring polynomials, or preparing for advanced coursework, this fundamental skill will serve you well throughout your mathematical journey.